Hi, as an introduction, actually, before we start doing anything, I want to give an example, which is a system that models predator and prey population. This model, it is called a predator-prey model. It is also called the Lotka-Volterra system. So this system is named after two people. To introduce a little bit of the background of this model, I want to share this story. So in 1926, you see this person who is an Italian biologist. Yeah, his name is Umberto di Ancona. He is an Italian biologist. He completed a statistical study of of different species of fish populations in the northern reaches of Adriatic Sea. And what he discovered was that during the World War I period, and the predator species was close to its natural state. But pre-war and post-war period, the population of predator is less. Yeah. So that means pre and post-war period, the intensive fishing might have disturbed the equilibrium to the disadvantage of the predator and to the advantage of the prey. So the intensive fishing, why it affects the predator pre-war, post-war period. So that is a phenomena the Italian biologist Ancona observed. And he came to his father-in-law. His father-in-law is a very well-known Italian mathematician of the time. His name is Volterra. So Volterra tried to formulate mathematical models to explain this phenomenon. So try to cast some light on the matter. So within a few months, Volterra had outlined a series of models for the interactions of two species or even more species. So Volterra could use his model to explain. And another person whose name is Alfred Lotka independently created similar mathematical models. So that's why the population model is named after two people. Yeah, they didn't know each other's work, but they worked independently and produced similar mathematical models. So that's why population model is called Lotka-Volterra system, also called predator-prey model. So now I'm going to share the form of a model. So next I'm I'm going to use a whiteboard to write the predator-prey model. So we often, okay, we use X, for example, as a population. This population, when it changes, we use the derivative. But X, for example, if it's a population of predator, right? It changes with time, so it's actually a function of time. X as a function of time. If Y as a population of the prey, it is also a function of time. They change with time. But if we want to study how quickly it changes with time, we use the derivative. It's the derivative of the function with respect to time. So the population or the predator-prey model, suppose X it represents the predator as a function of time, and the Y as the population for prey. So this X means the population. Predator and population of prey. So we have two functions. So each should be very clearly defined. So we here make sure that X, the meaning of X as a function of T is clear, right? The function of Y as the function Y as a function of T is also clear. And then now we can study the two functions. The two functions. So we try to imagine the two species if they grew as if each were isolated from the other, then suppose the predator without prey and also with the assumption that it's proportional to the current population, right? So we have this. But without food, it's going to decrease because the rate of change of the population X will be decreasing rate. So we have we have a coefficient that is negative. And so let's imagine Y as the prey. Prey without predator, assuming there will be plenty of food supply. And then, yeah, suppose that's an ideal situation. They can grow and proportionally, yeah, and proportional, the rate of growth is proportional to the current population. So we can have a C, which is positive, C as a positive number. So this is a very simple model as if predator and prey were isolated from each other. So as a result, the predator will diminish, right? Because it's going to exponentially decaying to zero. but the prey without the predator, it will grow exponentially. So you can solve this equation using your knowledge from the previous ODE course. So you can solve each one. So the first equation is involving x only, the second equation involving y only. So you can solve it. I will leave that as an exercise for you to try to solve it in this case. So A and C are constants. However, if we imagine the presence of predator will affect the prey, right? Because they eat the prey. So, but the presence of prey will help predator to stay alive because prey will be the food for the predator. So we can add, so X. So this term, because of the interaction or the due to the existence of the prey, then this interaction will help uh, the predator. That means the rate of change of predator will be increased. So B is a positive number. And what's the effect of predator on prey? That is X as a predator. An interaction between predator and prey, and will definitely decrease the rate of growth in Y. So we will have a negative coefficient, negative D. So here we have A, B, C, D, assuming they are all positive numbers. By putting a negative sign, meaning we have coefficients that are, this will be negative, B will be positive, C positive, negative D negative. But A, B, C, D are supposed to be positive, all positive, A, B, C, D. Okay, so now you have seen this model, population model, which is called Lotka-Volterra system or predator-prey model. Yeah, so that is the model. So I just make sure that we know the notation ABCD are all positive. Okay. So now we can look at a concrete case. So suppose I have X. So let's suppose the first equation, X derivative. If you want, you can simplify your writing. That is, you don't have to write the parenthesis t, because if you remember X is a function of t, and then you can simply write X prime, which means the derivative of X function with respect to t. So you can simply write that way. And then it equals, suppose A is 1, so negative 1 times X. If B is a fraction, suppose 1/10 xy. And suppose I have y derivative is equal to C is also 1, so positive 1. And xy with a negative coefficient and fifths, negative 1/5 xy. So if you are given this system of two equations, could you tell me which one is the predator? Yeah, which one, x or y? And remember x, you can put parentheses t to remind yourself x is a function, right? Y is also a function, although we don't write the parentheses t. And keep in mind, they are functions. We try to determine x and y, but the x, y will satisfy both equations. Therefore, we have a system. So you probably think, okay, so that means suppose without this interaction, you see this x, the rate of this x population will decrease due to this negative x, right, with negative coefficient. So x must be pre. That means without the presence of the predator, x must be predator. Without pre as a food, without this part, without y, the x has no food. So it will eventually decrease. So you see the rate of change of population will be negative. Yeah, negative times the current population. So the y must be prey. X is predator, y is prey. Because without predator, the rate of population will increase. So that means let's suppose without the x interaction with y, and then the y will grow, right, without predators threatening. So, but the reality is there is the threatening. So the predator will affect the prey, and the prey will help the predator survive. So because they're food supplied to the predator. So actually there is this system, and the interaction between x and y will will give us such a mathematical model. Yeah, so this mathematical model, if we study it, then we will be able to at least quickly find at least one simple solution. Let's assume the population x, this population is a constant, assuming it doesn't change with t. Can we possibly find a constant solution to this system? Suppose x is a constant. We just look for a constant solution, see if there is one. Why are we looking for a constant solution? Because the function is a very simple function, right? If x and y are both constant functions, they are very simple, maybe easier to find. So let's assume x is constant, then immediately the x derivative will be 0. The first equation will become this. And if y is a constant, the derivative of y is 0. The second equation will become this one. So then we can find solutions and for x and y. So let's let's try to solve this, try to get x and y. So what is x, what is y? And if we continue, so let's factor out x, right? I put 0 on the other side. So x is a common factor, so I can factor out. So the -1 plus 1/10 y. The second equation, if I factor out y, and also I put 0 on the other side. So the y is a common factor I factor out. So it's a 1 minus 1/5 x. And then we can see from the first equation, either x is 0 or y is, y is 10. From the second equation, either y is 0 or x is 5. So now how many solutions do we have? That means solution for the system, for the original system, is supposed to be the function, two unknown functions, right? X and Y. We're supposed to find X and Y functions. So we found at least one solution. You see, if X is 0, Y is 0, that is a solution. Or if X is 5, Y is 10, that's another solution. Yeah. So let's write so either x is 0, y is 0. That's one solution. Or x is 5, y is 10. That's another solution. So we can check. This is very easy to check if x, y are both 0 functions. Certainly, we can quickly see that the derivative of 0 functions will be 0 and every term will be 0, right? So this is certainly a solution. And let's check the other one. X is 5, y is 10. So suppose x is 5, y is 10. We can also check. So if you put a 5 here, the derivative of constant is 0, right? The derivative of y, which is 10, also 0. The derivative of constant, certainly. And then the other side, you put the 5, put 5, put 10, you get 0 as well. So on the other side, so yeah, 5, 10 will satisfy both equations. So we verified that we have two solutions, and they are very simple solutions. You see, those are constant functions. And these type of solutions we call equilibrium solutions. But probably we have other functions which are not constant. But at least today you have seen some solutions to a predator-prey model. Okay, that's the beginning. And through the population model, I introduce a system.